Okay, so we're going to move on to a topic related to what we were covering recently, namely power management. So this time around, I'm going to look at power management techniques which emerged in the desktop arena and then kind of migrated to laptops and things like that. And I guess the intent so much is not so much on the mechanics of it, but also the kind of issues that come up when we think about shutting a system down, and always a trade-off between the functionality that is lost because of shutdown and how you can keep the system retain some of its utility. So this was a topic which between I would say 2005 through 2012, there in that window a lot of what happened, and at this stage these are techniques that are part of the systems that we use. So, uh, so the main problem out here is the following: that oftentimes we basically continue to keep our systems powered up even when they are not in use. And this problem manifests itself particularly in desktop computers, where lots and lots of studies kind of showed that that even when power management had sort of been implemented in operating systems, people were not using it, and there were a variety of reasons. And I think to this date, a lot of this remains true. So, what some of these studies show is that even when clearly the machine was not in use, they were still remaining powered up. The sleep modes were rarely used, and I think that remains quite a bit true even now. And in many cases, power management was sort of disabled. So even some of the recent studies, like UC San Diego, their CSE department, just hundreds of computers left on all the time, and adds up to significant sort of power usage. So and the same thing is kind of true for a lot of other systems. So they remain up when they're idle, even though sort of they could be shut down. So there are many reasons behind this. Part of it is simply that power management required user intervention, and we tend to be often not diligent about it. Another issue is just disruption to our workflow. So wake-up latency, particularly with mechanisms like hibernation and all, were often pretty high. And the wake-up was often unreliable. That is, you'll put the computer to sleep, and then it won't wake up. And this remains true to some extent, even to this date, where many scenarios like Linux, for example, is notorious for having problems with power management. A lot of it is basically poorly integrated software and hardware. A very crucial issue is, and this applies to many settings, that we often want an always-on abstraction. And what I mean by that is that even though you might think that when I'm done using my computer, when I'm away, I'm done using it, the reality is that many of our applications are essentially making our computers act as little servers. That is, they still need to be on the network, be vigilant about something. So, for example, like last time I had mentioned Skype as an example, right? So we use voice over IP, we use Skype, Google Talk, these kind of things. And if you truly put your computer to sleep, then of course incoming calls are not going to work. So there is some degree of service that we expect our computers to provide. There are many other examples. You may be using your computer as a home media server, in which case you might be on a different sort of on your TV or something and trying to connect it. Again, the computer needs to continue to have a network presence. Oftentimes we are using these machines as gateways for sensors and all at our home. Again, they need to remain up. So somehow we want both the ability to sleep as well as the ability that the device be present on the network. At least it should be able to respond to this. Then there are other aspects which are more enterprise setting kind of things. Like, for example, in many companies, the computers are actively managed by the IT department. So you may leave the office. If you truly put your computer to sleep, then they cannot do like nightly patches of the operating system or things like that. So there is an interference with the workflow which exists in many enterprise settings. So, so what ends up happening is that for different reasons at home because of this network presence issue, at for these kind of services, enterprise settings because of the desire to do management activities, basically computers sort of are often kicked up. There are other examples, so like quite common nowadays are various kind of attachments that you hook up to your PC for cheaper voice over IP type services. So for example, various ways where through USB you plug an analog phone to your computer and then kind of making use of VoIP type services, Magic Jack being an example. The interesting thing out here is that you might save money on the telephony service, but then you may actually end up losing money because you're keeping a big PC up all the time with something like this. So, so in this particular example, Magic Jack, cheap service, you're saving on that side, but if you're keeping the PC up, you're burning a couple of $100 a year on typical electricity cost. So in a nutshell, what we would like to be able to do is put things to sleep, but still benefit from these network services that we are part of. So we still would want the PC to wake up when there is an incoming Skype call, or PC to wake up when I try to access the media library from different location and all. So I guess question for you, what happens on your devices? I mean, I see Anthony using a Windows machine, you're using the Mac. Do you guys know how is this issue currently handled? So you put your machine to sleep. Do you receive Skype calls? Or what about other network services? Or anyone else can comment on it. Like, what do you think is the state of affairs on devices you use?
I know that on the newest Intel motherboards, there is something like connected standby, I think they call it, where it's actually in standby, but it wakes momentarily occasionally.
Okay. Or what do you on the Mac side?
If it sleeps, then I think my status is automatically changed to idle, and I don't receive anything.
Okay. Anyone else who knows more about on the Mac side? So both Windows and Macs now do essentially what you are describing. So you should go to power management and explore your machines. I think it's a very useful exercise to learn the tools you're using. So both Macs first and Windows more recently, or whatever, Intel more recently, moved toward this model that even while you're asleep, it momentarily wakes up and sees, and I'll describe how sort of these things work out, essentially does enough to maintain connection with the network as well as presence on the network. And certain kind of services can therefore still be maintained. Okay, and the thing is, it requires support from the network side and all, and so and so forth. But like my laptop, for example, every so often wakes up quickly and participates in some networking and kind of goes down. And the Intel connected business is kind of in the same vein. Now, this desire or this need, yeah, go ahead.
Does Mac Mini participate in that?
Does Mac Mini? Yeah, all Macs in recent 2-3 years or so time frame do. But the way it works is that you need to have the supporting airport base stations. Okay, so it won't happen with an arbitrary system. Okay. So I'll describe later on how sort of these things work out. But this need or this desire was certainly not something that was entirely new, in the sense that even before power was an issue, or even before wireless was there, the notion that I should be able to wake a computer up on a network was needed, partly because of that enterprise management kind of thing that I mentioned. So what this was called was, and this is a decades old technology, something called WakeOnLan. And essentially the idea out here is the following, that on the Ethernet card they would have a very simple logic. So firstly, when you put your computer to sleep or even shut down, as long as it's plugged in, there was a tiny part of the Ethernet board which was powered up still. And then kind of the idea is that when a specially formatted Ethernet frame arrives, not an IP packet, an Ethernet frame arrives onto the Ethernet card, then it would wake up the computer. It literally controlled, you can think of it as it was a switch in parallel to the main mechanical switch of the computer. So, so on the board itself, just enough circuitry to recognize this specially formatted packet, and whenever that would arrive, and match the local MAC address of the computer, so you could target it. You can say a computer with a particular MAC address should wake up. MAC addresses in Ethernet are 48-bit, so I'm sure you would have seen those 6-byte long sort of MAC addresses that exist on Ethernet. So the packet would carry that. So essentially, the idea is that I can wake up a sleeping computer by sending out these WakeOnLan packets, WakeOnLan frames. But of course, I need to be on the same network, on the same LAN, because this is operating at the Ethernet level. It's not. I cannot wake something up in my home, for example. I have to first log on to something, and so that I have a presence, so that I have an ability to send an Ethernet frame on my home LAN, and then I can wake up something. So that's the basic idea. So those special packets were called magic packets, and there were a variety of sort of terms by which this basic capability was referred to. So some of them are there, but kind of the generic term is WakeOnLan. And the magic packet itself that I talked about, it's a broadcast packet. It's specifically designated that anywhere within its payload there is a 6 bytes of all Fs, followed by 16 repetitions of the target computer's 48-bit MAC address. So it's a very specifically defined frame, the listening computer kind of waits for it. Whenever it kind of sees it, says, "Aha, I need to be woken up," and then works on it. Like I said, it's at the MAC layer, so IP addresses, DNS names, none of those things have any bearing out here. This is purely operating at the LAN level. It was designed to be pretty simple, and remember, again, this technology has been around since 70s, 80s, so very minimal power consumption, yeah, so a whole bunch of stuff around it. So the way this would typically work is then you would have like an enterprise settings and all, there would be some sort of a gateway computer which is always kept up, and then you would log on to that, and then you say, "Wake my office computer," and then so through some sort of an interface, so you could send the magic packet out, your computer would wake up. There were other issues. For example, you send out this packet, there's no acknowledgement, so you don't actually know whether your computer is woken up. So you would have to, conceptually, after waiting for some time, you would try and see if your computer is now on the network. Okay, but that's how things worked. So that's the basic WakeOnLan. Problems started coming in where, as kind of the complexity of power management, the power states kind of went up. So, for example, there are multiple states that a machine may be in. So I sort of didn't go into it, but Intel classifies machines in terms of these various sleep states, as well as kind of there is a global mechanical off state. And WakeOnLan can handle some of them, not all of them. The time it takes to wake up from these different states is different. So what began to happen is that that simple notion, my computer has been shut down, wake it up, to now it began to have many of these it needed capabilities of handling all these different kind of states and all. So WakeOnLan sort of over time became more complicated. Now, ignoring that issue, there are several limitations from that basic strategy why it sort of doesn't suffice. So it requires that you somehow know the destination computer's MAC address. So, question: how do we know a destination computer's MAC address? What happens in networking if I send a packet to your computer? Usually I'm given your IP address, right? So where does the MAC address come from? the ARP protocol. How many of you have heard of ARP protocol besides Mustafa? Okay, so ARP is something called address resolution protocol, and what happens is the following. So let's say we are on the same LAN, like the EELAN or CSLAN, and I'm contacting your computer, so anthony.e.ucla.edu. Well, first step that happens, my machine contacts the DNS server, which returns to me the IP address of that machine. I'll realize that that IP address is on the same network as I am on, because basically it's a local address, so that I get to know. But I still do not know the Ethernet address, so I cannot send a frame to Anthony. Now, one thing I could do is do all transmission in a broadcast way, but that's extremely inefficient. So then the first thing we have to do is to find the MAC address, so that then from that point on, we can send a dedicated targeted packet to that one machine, or wake it up if necessary. So that is done by what is called as this address resolution protocol. And the basic idea is we send out a broadcast packet saying, hey, I'm looking for this IP address and need to know the MAC address for that. So anyone, including Anthony's machine, could respond to that. So for example, it could be that, I don't know, Jeremy's machine previously had communication, and it was sitting, that mapping was sitting in the cache. So his machine would respond. Or if Anthony's machine is up, it would respond. So someone will respond, and my machine will now get to know the mapping between that IP address and the MAC address, and then I'll store it in my cache, and I'll store it for a while, and then kind of discard it. So if you are on any of your machines, if you type ARP space -A, then it would show you all the IP address to MAC address mapping that your computer knows about. Of course, this has issues also. What happens, for example, if a machine changes its MAC address for whatever reason? Can happen, or under certain settings, or maybe the IP address changes. Maybe that machine decides to take a different IP address. So there are complications that one has to kind of deal with. So that's what the ARP protocol does. It provides a way for us to get the Ethernet address. But WakeOnLan needs that, so you have to precede it by kind of this ARP somehow. Third thing, you need the hardware support. Not all Ethernet card or Ethernet chips have that support. There is a security issue. Anyone can send that packet. So this is a form of a power attack. I left my machine asleep, but someone just out to cause nuisance or whatever, or perhaps more nefarious motive, can send a WakeOnLan packet, and my machine will wake up. Okay, so anyone on the LAN can send the packet. Now, it turns out that in some cases you could set a password, and there was a more complicated kind of setup, but not very commonly done. There is half the time these kind of things didn't work, so it's not a very reliable technology. Certainly, it was hard to get it to work from outside the local network because of its reliance on the MAC address. So broadcast packets are generally not routed. They are maintained within a local area network, because if we were to broadcast the packets, then they will flood the entire internet, and we'll have huge problems. So broadcast packets are not routed. So let's say now there is a technology in something called subnet directed broadcast. So the idea is that I could, sitting on, let's say, UCLA network, send a broadcast packet which is meant to be broadcast on my home network. Okay, so the idea is that I guess the packets are going out from UCLA, different routers at UCLA, back to our backbone, through whatever ultimately Time Warner cable, and then back to my home. Nothing intermediate is going to broadcast it until it hits the network of my home. The problem is that this nice clean abstraction doesn't work very well, because firstly, this particular subnet directed broadcast is not very widely supported. The other issue is, if you think about how, like, for example, things are home networks. Our home networks are not true public networks. We hide behind a NAT firewall or something like that, right? And so that creates a complication. My entire home is visible as a single IP address, Another thing is, we were to do a wake up or a broadcast above, then all Time Warner clients in kind of a general area are going to receive that wake up message. So not very satisfactory. So point is that while in theory this ability of targeting a broadcast on a particular network exists, and I could therefore sort of use that and then do a WakeOnLan on that remote network, in reality all these things come into it. The final technology you could use is VPN. So what I could do is I can VPN into my home firewall, for example, or back like my office firewall, and then have the firewall issue a WakeOnLan command to a designated computer. You could do that, but again, not a facility which is always available. So variety of limitations in this basic thing, but has, like I said, has been around, and if you're willing to kind of live with its pain points, then one could sort of at least wake things up. And no, it still doesn't solve the problem I started out with. I want to be able to receive a Skype call, okay? Because somehow now my router would need to know that a Skype call is incoming, and then arrange things to be woken up and send out a WakeOnLan, and then the latency is huge and stuff like that. So all those complications come into play. Now, more recently, so this thing was for wired networks, Ethernet. More recently, as in 4 or 5 years ago, this thing began to be supported for Wi-Fi, for 802.11 LANs also. So this went under the name of WakeOnWireless LAN. So it's a standard which got tagged on top of Wi-Fi, and kind of the idea is that we could have the wireless network, over the wireless network, have the same kind of capability. My laptop is asleep, and somehow it can be woken up by sending a special packet to it. Now, unfortunately, that is easier said than done, okay, because in a case, in the wireless case, if we shut down the radio, I mean, part of the reason is the battery issue and all, so we don't want to keep the radio up all the time. So I'm not in a situation where I can simply say, let's keep a part of my network interface up all the time. When a packet comes, I'm going to wake it up. That's not going to happen. So the way it works is that periodically the wireless network interface comes out of its standby mode and quickly checks with the access point whether there is a packet waiting for it, and then it goes back to sleep. So that is what the connected technology that you are talking about, and that's what sort of Macs do as well. So this was, I think, first introduced in a Wi-Fi chipset by Broadcom, but it's kind of a standard state that kind of wakes up. Now the issue there's some other additional complications also which come into play. So when we use Wi-Fi, our radios have to register with the access point, with a particular access point. And during that registration process, so like when you select SSID associated with an access point, what's happening is that there is also a shared key which gets established, so that the traffic between you and your machine and the access point is encrypted from that point on. And then that key has a validity of some time, and if you fail to connect, then the access point is going to kick you out. So you cannot simply go to sleep for long duration anyway, so you have to maintain this registration with the access point as well. So all those issues got sort of addressed as part of this WakeOnWireless standard. So essentially association with the base station, PSS, is maintained. The network card has to come periodically out of the power save mode. And to maintain kind of registration with the access point. Now, clearly, in something like this, in these kind of devices, you cannot have a true hibernation or a full power off state. You have to keep this basic functionality alive. You have to periodically wake up, renew the registration, check for any other traffic, kind of go back to sleep. So the WakeOnLan kind of stuff is not there, but we kind of fake something very close to it. Moreover, your access points explicitly have to support it. So for example, you need to make sure that packets can be broadcast, and all, which again sort of oftentimes is not done. And the wireless adapter needs to be integrated with the motherboard. Okay, so this doesn't work. For example, if you have a Wi-Fi USB adapter, which you kind of plug into the USB, it won't work with that. It has to be something which is on the motherboard so that the power can keep getting supplied to that. So this technology sort of got introduced and is kind of the basis for the way power management together with network connectivity is kind of done. Going back to this kind of illusion of connectivity, I mean, I'm sure one of the things, I don't know if you've noticed or not, but like current generation laptops, even when you put them to sleep, you wake up in the morning, you lift the lid, and your emails are all which arrived at night, which are there. It's not that it's getting them very quickly, it's that it was periodically checking it. Okay, so that's kind of the norm. You can disable these things, again, go to the power management thing, but the norm now is that they try to give this illusion, or like your phone or the tablets and all, similar notion now that you can set applications. I'm speaking more on the Apple side of things, but I'm sure Android has something similar, that applications could be set so that they can keep fetching the content, as they call it. So the idea is, my phone has been asleep for a long while, but I open the New York Times app and I would have the latest news. It's not that at that time it will have to go and fetch it. So those are all kind of variants on this issue that somehow between making the radio more efficient and all, we can kind of periodically wake up, fetch the information, give the illusion of being connected while still sleeping most of the time.
Have you gotten this set up for yourself?
It's standard on Macs, and like I said, that as long as you stay within the Apple ecosystem, it's automatic. So, like for example, my home and office are both using Airport base station, so I get it automatically. And I'm pretty sure Intel's technology is again similarly tied to certain access points supporting it.
Have you actually done the wireless WakeOnLan yourself?
Yeah, it's there. It's automatically there. I don't have to do anything.
I mean, have you manually like brought it like to on from off like for actual use?
Yeah, you can turn. So it comes on. You can turn it off. Okay. Okay, you might be right. So for me, so every time I get a new machine, I just transfer the old machine's configuration to a new machine. So I never notice it. It's possible that it was by default off. But basically, you can basically set things up, and also on like phones and all, you can even do a per app by basis. Like you can say this app should get the content and not the other app and all. Okay, so but they're all kind of relying on this underlying basic. Yeah. Question.
What's your experience on Apple Watch in terms of the WakeOnWireless?
I haven't had much time to play with it, unfortunately. I'll report on it in a future lecture. But the battery lasts long enough. That's good enough.
If you go back 2 slides or 3 slides to the Magic Jack, so actually the Magic Jack, it's this thing.
Yeah.
So apparently, my dad actually uses this.
Mm-hmm.
So they updated their hardware. So now what you do is actually the Ethernet plugs into the device itself, and
Okay.
you can plug into a wall outlet.
Okay.
So now you no longer need your computer to be on all the time.
Sure. So for all these devices, there are many different variants which are out there. You're right. So like for example, take Vonage, which I use at home. Okay, Vonage Sensio adapter, which hook up to Ethernet. That's the one I use. But they also have a USB one. Okay, but even I don't think the one I have with Ethernet ever goes to sleep. It's always on device. Yeah. But you're right. So you could have Ethernet-based thing coupled with what? They'll probably still need this WakeOnLan doesn't quite work out, but there could possibly be other ways of doing it. Yeah. So WakeOnWireless is kind of the newer take on WakeOnLan, and mostly because the devices where we care most about power happen to be wireless, so it's important. So to summarize kind of the problem part of this, essentially this inability to successfully sleep kind of essentially runs counter to what our stated goal has been, namely to do nothing very well. Okay, so the energy proportionality argument, and sort of a key culprit is that increasingly we want our devices to have network presence, but we also want them to go to sleep, and that's kind of the issue. So the challenge really then comes up is that how do we maintain this network presence? And the WakeOnLan was kind of like I said, you can kludge with it, but it's not a very satisfactory solution. And same thing with WakeOnWireless, where it's sort of is certainly part of the solution, but not in itself the complete solution. So to maintain network presence, and we'll see it's sort of a complicated issue, we could go around redesigning protocols, the entire TCP/IP stack, but not very easily doable. Another idea is, and this is the notion of having a proxy. So the kind of the idea is you go to sleep, but you designate someone else to represent you, okay, and be the network, maintain some degree of network presence on your behalf. And that someone else could be, for example, a virtual machine running in the cloud. That someone else could be some piece of software on your home gateway. And so the idea is that when it comes time to be woken up, there are a couple of things you can do. Firstly, simple things which need to be responded while your main device is asleep could be handled by the proxy. And then the other issue is when the device does need to be woken up, because maybe some user interaction is needed and all, then the time that is needed to wake the device up, during that time, this proxy can continue representing you and wait until you wake up, kind of hide the latency. So this concept of proxy is very well established now. So this proxy could be, like I said, something in the cloud, something in the network infrastructure, could be another machine which you always keep up. All these solutions people have kind of explored. Just to put it sort of cut through things. So like the Apple solution, the reason I said it only works with their base stations is because their base stations act as proxies. They can actually take care of a lot of services on behalf of your sleeping computer, and so that when your computer next wakes up, then it can deal with it. So that's kind of the concept. Because one thing to remember in radios, there is no such thing as that I can wake up a sleeping radio. If the radio receiver is asleep, I have to wait for it to wake up. I cannot magically wake it up by sending it anything, because by definition, if the receiver is asleep, it cannot receive any energy from me. There is a related concept that people often try with wireless, which is the notion of having a second radio, which they call as a wake-up radio. And the idea is that this is some very low-power radio channel, separate radio, and then what we'll do, and that's always on, and you kind of send a packet with that, wake it up, and then you wake up the main radio. Okay, so that's how you kind of fake this. And if you Google for wake-up radio, you'll find there are a few companies which kind of even sell these things. So these are very tiny chips and all. For certain settings, they are fine, but it's not a widely adopted practice, and you run into all sort of issues like the range has to be adequate, and things like that, and sort of there are obviously cost implications too. So back out here, we could redesign protocols, we could encapsulate whatever presence we need into a proxy and kind of do it. Currently, mostly because of that, it's not easy to just go out and say, okay, we are going to redesign the TCP/IP stack, and voila, it's done. It's not. It will probably never happen this way. So all solutions that you see are in some shape and form based around the second strategy, which is the proxy. So some entity which is maintaining the network presence on our behalf, and so to other devices, the sleeping device appears to be operational. Okay, so you will on your TV, when you are looking at your media library, it will appear as your computer. Actually, you can see your media library and stuff like that. It's just that your computer is asleep, your base station or something else on your network is acting on its behalf. So proxying is a concept which is now well established in the standards. So I mentioned the EPA, Energy Star and stuff like that last time around. They officially kind of define this capability. So proxying refers to a computer that maintains full network connectivity. For a system to qualify under proxying, it must meet a non-proprietary proxying standard, and there are certain such standards which have been approved, for example, by EPA, by European Union, and so forth. So there are standard ways by which proxying can be done. And another definition out here, a proxy is an entity that maintains network presence for a sleeping high-power ICT device. So these are all kind of concepts. And taken to the extreme, you could imagine the ultimate way of proxying is that your computer is nothing but a virtual machine running on the cloud, and it's always on, it's always doing things, and you can put your machine to sleep, but it's nothing but really a display device. Okay, what I mean by that is that you could run Android virtual machine or an iOS virtual machine or a Linux virtual machine out in the cloud. It's always running. It's sitting in some data center, and then my laptop or my device is nothing but a display for that. And so like for example, maybe you are running something with VNC or remote desktop or these kind of technologies. I'm sure you may have used these things at different times. So the idea is now my device is truly stateless. If my device is stateless, then going to sleep is easy. Okay, nothing needs to be done. Now, it still doesn't solve the wake-up problem for my Skype issue, right? I mean, if there is an incoming call, that virtual machine can do everything in terms of handshake and all, but it still needs to make sure my device wakes up and presents me with the user interface and with the sound in and out capability. But having that VM out in the cloud always there is certainly one solution, and many services now kind of essentially do that. I mean, for at least sort of through Amazon Elastic Computing or DigitalOcean or these kind of things, you can always just have a computer running out in the cloud, always on, never worry about it. But the I/O with the user, the UI part remains unsolved. So how does proxying work? So conceptually very, very simple. Host is awake, it becomes idle at some state. So when it decides it needs to go to sleep, then it's going to transfer its state to the proxy. Proxy is going to respond to the routine traffic for that sleeping host. And under certain conditions, when the user interaction is needed or some resource on the sleeping device is needed, then the proxy is going to wake up the host. So those are the steps. Host goes to sleep, it dumps its state into the cloud. It dumps its state to the proxy. From that point on, anyone wishing to contact the host is redirected to the proxy, and it interacts with the proxy. At some stage, the proxy realizes, I really need the user interaction, or hey, I really need some information or resource which is only on the host, in which case it arranges for the host to be woken up. So, sounds very simple, but there are several tricky pieces out here. So, one is this device went to sleep, now the proxy has to take over, right? So, if you think about it, how would that happen? Somehow, because the host out here, it knows the IP address. Somehow that traffic has to be routed to the proxy. If the proxy is on the same LAN, that would be easier. If the proxy is somewhere else on the planet, it's going to be a lot harder. So that's one issue. The second issue is, how does the proxy make this thing up? That would be to be handled. So behind this simple handshake, there's going to be a lot of these subtle sort of issues which are going to come up. The proxy itself could be a totally separate entity, a box on my LAN, a box somewhere else in the cloud, or it could even be something which is some part of my network interface which is always up. Okay, so it could be any one of these capabilities. So proxying in standards. So probably the very first attempt at standardizing proxy and all was something called ZeroConf or zero configuration. This is a technology that Apple started pushing back in like 2005-6 kind of time frame. It is what is called Bonjour now. So if you have ever, those of you with Macs, if you notice sometime in the browser you see kind of Bonjour thing. So that's kind of Apple's name for it. But ZeroConf is a standard which is out there. So what it does is that they basically make different services that a computer can handle, that is, when it can act as a server. They make them into services whose presence is advertised through this particular protocol in the form of these bonds messages. So you can contact a host and say, or you can ask what all services it has. So the host has a list of services. The services could be, you can talk to me through SSH. You can connect to me through FTP. I serve iTunes libraries, or so all any kind of service that the host is willing to accept. It basically advertises. So there is a registry someplace conceptually where the host puts that information saying all these services I'm willing to listen to, and then any party who's interested in that, it kind of contacts to that. So what they do out here is that using that wireless wake-up technology coupled with this bundle, essentially what happens is that when a host goes to sleep, it basically transfers the responsibility for advertising its services to the base station. So the base station also has that service advertiser, and it knows that this wireless, like my laptop, is going to sleep. So then the proxy on the base station takes over and advertises on behalf of my laptop. So what Apple does is it provides, remember this is kind of that closed wall environment, so there are certain things that they could modify and support. So for example, R, file and print, SSH, all these kind of services, they already provide support for. So I could, for example, my laptop could be sleeping, and from another machine on when I do SSH into it, essentially the initial handshake gets taken care of by the base station, and meanwhile, a little bit later when my laptop sort of wakes up, it basically kind of takes over. Or like, for example, file and print services. So like when some computer on the LAN says what all printers are there, and if there was a printer attached to my sleeping desktop, it would still get advertised. So others can still discover it, and then kind of the wake up happens. So this was one standard, and like I said, Bonzor is Apple's name for it. ZeroConf is kind of the official standard name for it. The other proxying standard is through the standard body called ECMA, and it's called ProxyZZY. Again, kind of the mission is similar: maintain network connectivity and presence to extend sleep duration, and this is what is behind the UPnP, which is sort of Windows. I'm sure you've probably seen UPnP printers and stuff like that and all. So that's what happens on this side of the world. So there's a proxy notion there as well. So let's look at an example of how SIP, which is one of the ways IP telephony is done. There are several different IP telephony standards. One of them is called SIP. So SIP catcher is one of the technologies out there which lets IP telephony work while still sort of things may go to kind of sleep. So the kind of the idea is that there is a proxy which knows how to handle the SIP protocol. It wakes up the IP phone as needed, and it knows it's enough state. So the proxy, so the proxy could be running, for example, on my home gateway, and the IP telephone can go to sleep. Or in your example, the Ethernet-based magic jack that you were mentioning, it could go to sleep, but then something on the home gateway or the router kind of handles stuff. So when a caller calls, this guy will handle stuff, and meanwhile kind of arrange for it to be woken up. So conceptually, it works something along the following line: that the caller calls the SIP service, let's say Vonage or something like that, which sends the invite packet. The SIP catcher running on the home gateway will catch it, and it knows that it needs to wake the IP phone up, but that's going to take time. So what it does is it does partial realization of the SIP protocol. It sends back a signal saying trying. So this is the equivalent of the ring we are ringing. So that this guy is happy, and then meanwhile it sends the magic packet to wake this guy up, followed by the SIP packet, and then things happen. And essentially, what is happening is we're kind of just delaying the whole protocol to take into account that this guy was So, so there's, as you can see, kind of the proxy out here has to be aware of the particular application. If this was something else like Skype or something, then there would be a different set of messages. So this is not some general purpose kind of thing. It will have to have knowledge of specific application handshake and also that we can keep things up.
So this is why the home routers are becoming more and more expensive.
I don't know. They are becoming more and more expensive to make you buy more and more expensive stuff. I mean, that's I think a separate kind of reason. But part of it is yes, there is what used to be a simple router is now a whole bunch of other things. I mean, it's a firewall and doing all these other shebang. Okay, I mean, they are essentially full-fledged hosts which just happen to also do firewalling. Yeah. But you would see that a lot of them advertise these kind of services. They basically are putting application intelligence into these boxes in order to be able to support these kind of capabilities. So that's the example of the SIP catcher. So one of the ways we could also put this kind of capability, this kind of proxying capability. Remember, a proxy can be in many places. Like I said, could be in the cloud, could be somewhere in the LAN, but could also be part of the network interface card. So some work in recent years out of Microsoft and UC San Diego, they kind of explored this route quite a bit also. So the idea is that they basically sought to augment the network interface so that PCs can respond even when asleep for a variety of different kind of protocols. But the idea is that, and you do not want to make any change to the rest of the infrastructure or to the user behavior. So this was one attempt at it. So kind of the idea is, let's imagine you have a PC, not very atypical power numbers, but the main point is there's a big difference between idle and sleep, so you want to put things to sleep. So what you now do is, in your NIC, you have a secondary processor. So remember, previously I talked about in WakeOnLan, there is some part of the NIC which is always on just to intercept that magic packet. Now imagine that part on steroids. So what we have is actually a secondary processor consisting of some low power CPU and some ability to some memory and all, and therefore some ability to do some more meaningful thing than just checking for a magic packet. So these guys in particular used a device called Gumsticks. Anyone heard of it? Gumsticks? Okay, so you're shaking your head. So Gumsticks shown out here is a tiny chewing gum sized Linux ARM-based device running Linux. Okay, so it's been around for a while, sort of rather popular. So basically, what they do is they use sort of Gumsticks to device as kind of a secondary network interface card. So kind of the idea then is that my main CPU has the main network interface card. When this guy goes to sleep, we transfer the relevant state out here so that it can then fake being the PC. And since it has its processor and stuff like that, it can continue to participate in the application protocol. It can do all these stuff that we wanted. So this was the idea behind this work called Soliloquy out of UC San Diego and Microsoft. So essentially, what happens is on the main processor, main host, they have a Soliloquy daemon that is running, and then they attach to the main host the secondary network interface with its own processor. And then essentially what happens is that on this processor, on the secondary processor, they run some embedded operating system and all, but very importantly, they run some pieces of the applications out here. So the idea is when things go to sleep, the state is transferred out here, but applications also can put stubs out there so that an application in effect has kind of, you can say, a subpart which it can designate and say, this needs to continue running even when the PC is asleep, okay? And that part kind of runs out here. And then there is some other stuff as to, for example, telling this guy what ports to listen and all, and then, of course, software to kind of hand state back and forth. Okay. So that's kind of the basic concept. Go ahead.
What is a submilliquid there?
What does somniloquy stand for? Anyone with better English than mine? Okay, anyway, somniloquy refers to sleepwalking or sleep talking. Sorry. Somni is sleep, loquaciousness, talking. So somniloquy, talking in sleep. Okay. So that's kind of the idea. Okay. I don't know whether it's a real word or not, but that's where it's coming. Okay, so they're designing a system which can blabber in speech and sleep. Okay, that's kind of a concept. So this was their prototype. Okay, so they basically kind of hooked up this gumstick-based system and kind of tied together. And kind of the idea is that this can kind of take over things on behalf of the main host. Okay, so. Those are details I'm going to skip over. So essentially, you start out with these kind of two systems. Applications running here, but applications also have stubs running on this secondary thing. And I mean, they had an ugly looking prototype, but imagine that this was actually something on the motherboard. There's some liquid daemon which is running out here. It keeps track of what the network configuration is. And then what happens is when it comes time to sleep, it is going to basically migrate state. So by default, we are operating in this mode. This guy is asleep. The main host is up. At some stage, we decide that we are going to go to sleep. So at that time, application state is migrated along with certain wake-up information is sent out. Also, port-based wake-up filter. So we need to tell this guy what all to listen on because there's a large space of TCP/IP ports that exist, but we are interested only in certain of them. So this basically says what ports should be woken up. So kind of the idea is the following: that at any given time on your machine, there are applications running which are listening on network ports, and those are all that matter, and nothing else kind of matters. So, and if you ever do netstat, then that shows you on Linux. If you do netstat, it shows you the list of all the applications that are listening on some particular port. So that information we need to set out here because you don't want this guy to, anytime it receives a packet on any arbitrary port, to wake up the main host because there may not have been any application which was listening for that. So we transfer that state as to what ports we are actually interested in out here, and as well as current other network configuration information that we need, like routing tables, ARP tables, and stuff like that. So we can transfer that over, and then this guy wakes up, and essentially this is now working as a lower power kind of version of this thing. Now, at this point, so I'll come to this thing. I think I'll seek your opinion on these things, but we transfer responsibility to this guy. Then at some stage, what happens is that we need to wake this guy up. Now that can happen for one of two reasons. One is I received a packet, this little guy received a packet, and it doesn't know how to handle it because there is no application stub for it. In that case, it has to wake up the main host because there is a server process which is running there. Another possibility is that something arrived, the application stuff was there, but the application stuff is no longer able to handle that request. Okay, maybe it requested a file which wasn't there. So like some of the things they did was they would cache popular files and all out here. Okay, with the limited memory they had, and any request for handling those would just be handled by this. Otherwise, they would go out there. So. So at some stage we decide to wake things up. So we send out the wake up signal, and at that stage, this kind of takes over, and the whole process continues. And pretty impressive looking numbers that they had out of this. So kind of you can do sort of the obvious analysis in terms of what the power saving is going to be. Let's see, where are their numbers? Yes, okay. So this is written numbers. So our main point is that while running somniloquy, they can basically come close to being as if they were fully asleep, but still maintain this network presence that we were kind of arguing for. So whereas the other alternative is to kind of keep things in an idle state, and therefore you can continue kind of doing this. Now, I guess the question that I would ask you is the following. So this was as it was around 2010 or so. We are 5 years from then. If you were to try to implement something like this now, how would you approach it? What other technologies have come since which might simplify creating this kind of a concept where you can have some minimal presence, but still kind of still go to sleep? And something we have discussed, that's why I'm asking. Cloud brings a whole bunch of other baggage, which this guy doesn't, right? I mean, the moment we go to cloud, and we'll talk about it a little bit later, your whole wake up stuff becomes super complicated, right? Because now your wake up is going to happen over the network, whereas here, the wake up is happening locally, right? This interaction is local, and therefore wake up and state migration and all is a lot easier. If this guy was sitting out in the cloud, certainly a valid operating point, but that's not the one I was driving towards. Let's say I want to maintain this guy locally. Does it remind you big, little, big dot little, right? I mean, that's basically, these guys are faking big dot little before big dot little existed, okay? So now if you were to do this thing, I mean, the logical way of doing this stuff is going to be that this is just one of your little codes. In fact, the processor they are using out there is not very different than what the low-end ARM processors are. It is a low-end ARM processor. So the right way of doing this thing now would probably be, it's really basic, saying that I have a system which is very scalable. And it can have all the big cores running, all the up cores running, and then kind of migrate it. Because if you think about it this way, what is the difference between the two sides? It's really on the processing side. Both of them still are engaged in networking, so that power consumption is going to be is going to be similar cost. Okay, it's not that your Ethernet interface here and the Ethernet interface here is necessarily very different. It could be, for example, nowadays, what's the latest generation of Ethernet? How fast do our computers go?
Are we at 100 gigabits?
Okay. Yeah, 10 gig is the current state of the art, except that the network adapters burn maybe like 50 watts or something like that. Okay, so more typically what you will find is 1 gig, which our sort of computers use all the time. You could imagine that maybe this guy has access to a faster network interface, this guy doesn't. So, but you could perhaps still design for it that way. You can have a multi-core big dot little architecture with two network interfaces, and you activate one or the other. Or you could do the equivalent of frequency scaling, namely speed scaling of the Ethernet. So you could disable the 10 gig mode or the 1 gig mode and kind of operate it at. So not only can you dump stuff onto the little core, one little core, everything else is asleep, but you could also designate, sort of artificially limit the speed. The other things you can do is, again, relatively standard technologies, I can bring down parts of my DRAM. So what I could do is, if you have multiple banks of DRAM, you can disable power, put some of the DRAM banks into low voltage, just retain your state mode, and then do all the work with one of the DIMMs. So so the takeaway from this work is not so much that the particular signaling they are doing or the particular hardware they have, which is pretty ugly even from that era, but the fact that you could now realize something like this if you were to create using big dot little plus DRAM bank levels, power management, plus some scaling of the network speed. Okay, so that would be kind of the main thing. The precise numbers and all, since they are 4 or 5 year old, are not that relevant at this stage. Capabilities are kind of interesting. So what they do is, while they go to sleep, they are certainly minimizing the kind of stuff they could be done. So the claim is not that an arbitrary app can write a stub. I mean, certainly won't. But what they did was they wrote stubs for many apps. Okay, like for example, incoming Skype call, remote desktop request. I have a PC which is sleeping from my home. I'm trying to connect to it. I want the remote desktop. So for the main part out here is the following: that applications, there are many applications where they require a state to be maintained. Okay, that is the both part. There is state information, and therefore, if I were to restart the application, I have to reconstruct that state. And with the stub, they could make that happen. Okay, it's a much more seamless kind of transaction. Now, another thing you could ask for something like this is following. So they have these stubs and all. And kind of what's happening is this thing is therefore reasonably complicated. The stub is running and it's handling stuff. You could also imagine another possible point in this design space. What if every time a packet came out here and it matched one of the ports where I know we are listening in, we were to just wake this guy up. So no stubs, essentially. Every time it's coming up, we wake this up. That in effect is the choice that Apple made. So Apple's system that proxy system described kind of did that. So relative to that, the big addition out here is this notion of a stub. Interestingly, which one wins out is kind of a tricky question to answer. These guys obviously believe that having the stub justifies the additional complexity, but you could also make the argument that keeping this thing super simple, so that all it does is filtering based upon ports, and then kind of makes things up. That would be another design point. I've not seen any work where kind of they compare which one does better. Okay, so that's the soliloquy approach, but kind of main thing is that by shutting down the big resources and having proxy as a very lightweight embedded resource on your computer, you could make things come close to being as if you were sleeping mode, but you were still maintaining network presence. So this work had received a lot of attention, partly because Microsoft made a lot of noise about it also. So okay. So that was proxying by a local entity, something on your computer, on a network interface card itself. Another approach is proxying by an external entity, and we heard about perhaps we could do it on the cloud, or we could do it on another device like a gateway or a router, or one computer on my LAN, which we always keep up. So this partly is an issue of economics. So if you think about, let's say you're a large enterprise, like, I don't know, a company or a school of engineering out here, the savings from any given single machine are going to be tiny. Okay, if I can put them to sleep and all, over the year, I would probably save $50. But it's the aggregate which is enticing, that if I multiply this by a few thousand, now we are talking real savings. So in the aggregate, kind of numbers are, you can save maybe a couple of $1 billion across the 40 million enterprise PCs which are out there. But for any given company, the savings are relatively modest. And then when you compare it against a system administrator costing around 250K in salary and overhead and stuff like that. So now suddenly one issue which comes up, any sleeping solution which introduces a management cost which is per PC can force me to then put additional system administrator resources and then negate the whole saving purely in terms of dollars. So in particular, if we have this additional operating system with its additional application stubs and things like that, these are going to have an indirect cost, namely someone has to maintain them, and if each local device has this overhead, then my system administration costs are going to scale up. So the argument against having a local proxy is that it's not very friendly in terms of scaling cost-wise. So it would be better if we could have the proxying function as a centralized service, so that the additional system administration cost is not that much. So that's kind of the logic out here, that augmenting NIC, namely the soliloquy approach, besides kind of costly hardware, has administrative costs, someone needs to set them up and all, and so whatever modest saving we may have on enterprise-wide, if I have to hire a few sysadmin, that cost that advantage disappears. So that motivates towards this concept that what if proxying was a network service? Then it could be centralized. We can basically scale it much more easily across a larger number of devices, but it introduces its set of issues. So could we have a single dedicated proxy server for a large number of machines? First question, where should you place it? You could place it on a separate machine. You could place it on a switch or a router. It's very hard to place it outside the subnet. And this has to do with the way routing works on the internet. So let's say my machine with its particular IP address on the EENet, we decided to put it to sleep for a while, and the proxy is, let's say, out in Amazon's data center. Then suddenly that machine on Amazon's data center has to act as my machine's IP address. And so it's outside. Let's not even go that far away. Let's say we decided that EE and CS departments cooperated, and some machine on the CS network kind of is going to act as the proxy for everything in the school. Well, suddenly my IP address traffic needs to go there. Everyone else's IP traffic on the EENet needs to continue coming to the EENet, and that requires some sort of a redirection happening, and that's not easy. Because the way internet routing works. So, anyone knows how packets get routed on the internet? I would like to describe very brief. Packets on internet get routed, like when I send, when some machine on the East Coast is sending a packet to a machine on the EE network. What happens?
Basically, each router looks for either lookup table for the next route.
Okay, but what part of the address does it look at? Does it look at the entire address? Does it look at only part of the address? Yeah, so it looks at, so the routing tables basically are going to, for certain number of upper bits, it's basically going to show what next hop to take. So it may say any address which is of the form 128.56. Don't care after that, should go to this particular router. Okay, so it basically uses some k upper bits. At any given stage, some k upper bits are used as a network address, and the remaining we don't care, and then we say to reach any host on this network, go to this node. And then that node repeats the purpose with perhaps a different number of upper k bits. So it's a hierarchical routing kind of situation. We do not maintain routing tables which are for the entire IP address. So it's not my particular machine's IP address is how to get to it is not known to anyone. On no one's routing table would it show that my machine 128.97.xyz, that entry doesn't appear. What will probably appear is 128.97. That's probably being advertised, or perhaps something even coarser than that. So when it comes time to redirection, if we just want to redirect traffic for one machine, that would mean that somewhere on the routing table, now there will need to be made an entry for my machine's entire address, 32-bit address, or if it's IPv6, even more bits. And that can become very rapidly non-scalable, because the reason the internet routing works so efficiently is because it doesn't look at the entire address, it looks at only the upper part. So the routing table is quite short. But the moment we start getting into these things where one machine moves away and now I need to give that special treatment routing wise, then, and if that becomes a general case, that is machines are going all over, then my routing table size is kind of going to blow up. So very hard to put this proxying service outside a subnet without causing these kind of scalability issues. But anyway, but this is a problem not unique to WakeUp. This is a problem which is also faced by so-called mobile IP. So the mobile IP concept is that could I be anywhere on the world and my laptop contains a UCLA IP address. Okay, so you would be able to reach it through. Now that's, if you think about it, it's pretty difficult to do. I might be visiting some other institution and their DHCP server gives me an IP address, and now I want to fake it as if my machine was still at the UCLA IP address. It's not easy to pull off, and while people have proposed all sorts of solutions and all, but nothing really kind of caught on. So So let's talk about where then the network proxy servers could go. So we could place the proxy as a give me a sec. Yeah, so we could place the proxy as a separate box. So conceptually, what I'm showing is there is a remote user which wants to connect to one of the machines out here, and that machine is on the sleep. So I could have a proxy as a separate box. I could have proxy as a piece of software inside my router/firewall. I could have proxy in the switches in the network, and let's see what is happening. Yeah, okay. So they all have their pluses and minuses and stuff like that. Okay. Clearly, proxy is a separate box. It has its advantages in the sense that I don't have to mess with any existing infrastructure. I want proxying functionality. I just buy this little box, attach it to the network, and still get lots of benefits. Proxy inside the router, basically sitting at kind of a logical point. Switches is another possibility. Okay, all of them basically offers advantages. So proxy in a LAN switch was one of the earlier approaches people had explored. Part of the reason is LAN switches are always on because that's the heart of your sort of basic Ethernet connectivity. So it has the natural ability to intercept all sort of packets and work on it. So goals for a proxy. So what would such a proxy do, irrespective of wherever we put it? So it has to let the host go to sleep and not lose the network presence. So one of the issues that we'll have to maintain is that somehow IP address has to be maintained and remain reachable. So if my laptop goes to sleep and some other remote host tries to reach my IP address, it pings it, it SSHs to it, whatever, it should still appear as if my machine is up. Valid TCP connection requests must be honored. So some application remotely tries to open a TCP connection to my machine, that should still go through. Existing TCP connections should not be dropped. So it's very common nowadays that applications maintain a persistent TCP connection. So they open a TCP connection, not much traffic may be going through it, once in a while something goes through it, but the connection is maintained. You do not want that connection to get dropped if I shut down my machine. So the idea would be, let's say my desktop computer at office, I SSH into that desktop computer from home, and I have that open in one of the windows, and now I go away and no activity on my desktop computer at office, so it's put to sleep. And some proxy on CSNet takes over it. When I come back, my machine will be woken up, and we want the SSH session to be still active as the way it was. Now, so that requires that TCP connection should not be torn down. So somehow we need to make sure that happens. UDP packets sent to the host must not be lost. UDP is a trickier one because there is no notion of connection, and it's intrinsically a loss. It doesn't make any promises about perfect delivery. But what we still want is if someone is sending me UDP packets, they should not be lost. Partly it's important because a lot of media type traffic makes use of UDP. SIP makes use of UDP, a lot of multimedia type stuff. Remote state must be maintained. So application. So essentially all of the stuff that SomLiquid was doing. That we want the illusion as if our machine never went to sleep. And by the way, we would like to do all of that without causing any changes to network application and protocols, because any solution which requires telling that, okay, all applications need to change or protocol needs to be changed is not going to work because we would have huge amount of compatibility issues. So that's kind of the challenge, that proxy somehow needs to do all of this while not requiring anything to change. So that's kind of the challenge. So supporting IP connectivity. essentially boils down to that there is a small suite of protocols which the TCP/IP stack relies on, and we need to be able to continue supporting it. In particular, the proxy needs to take over the IP address. We need to make sure that the underlying protocols are DHCP and ICMP. Anyone know what ICMP stands for? Yeah, and what does it do? What is it used for? Yeah, so ping is a very common example of, okay. There are certain other things which also kind of rely on that, but this is, so our internet really is made up of 3 different protocols conceptually. There's TCP, UDP, which run on top of IP, and then ICMP, which is really kind of parallel to the IP, okay, and it's it's a control signaling protocol. So all of this need to continue working as they work, and by the way, should also work behind NAT services, which are just so very common. Now, supporting TCP connections. So the way TCP works is that the connection needs to be established. So the entity which is establishing the connection sends out a packet requesting a connection to be established. There's kind of a handshake which happens. So somehow we need to make sure all of that happens while, and even with the sleeping machine and the proxy taking over. We need to be able to maintain permanent TCP connections. So like I was saying, that when my machine wakes up, it's as if nothing happened. This connection starts from wherever it left off. So any data which had arrived meanwhile should get buffered, and so on and so forth. And then this should be TCP. So somehow proxy kind of needs to make all of that happen. And on the UDP side, again, we need to be able to buffer the packets and stuff like that to again minimize the effect of this. And application should basically not notice anything. The main point is we want a proxy which is totally transparent. Now that goal, as we will see, is extremely hard to achieve. So there are approximations to this basic goal that have appeared. So one earlier work in this space is again out of Microsoft, and it's called port hijacking sleep proxy. And the way it works is the following. So this is a client side. It consists of a proxy which is running on some machine, and then there's a client side stuff. Okay. So what the client side service does, this is some background job which is running. It sends information to the proxy server about all the ports on which the client is listening. So every time you run an application which results in the application listening on a UDP port or a TCP port, that information gets there. And it's otherwise running in the background, and it also keeps track of what is happening in by way of sleep request and all. So what happens is, like the user may say, put the machine to sleep and all. So this client side daemon running on your laptop or desktop keeps track of this. So the moment it sees this machine is going to go down, it basically starts a negotiation with the sleep proxy. What the sleep proxy does is the following. It responds to all the traffic relating to IP address resolution. So the ARP protocol that I described earlier, and there is a newer protocol called neighbor discovery protocol. So it basically works with these protocols, makes sure it responds. So it takes the ownership. So kind of the idea is, if anyone says, I'm looking for the IP address of this desktop which went to sleep, the proxy is going to respond on its behalf. What it further does is, it wakes the client which is sleeping, on any incoming TCP request. And these incoming TCP attempts are recognized by a special flag in the packet. So it does that. It ignores all other traffic. Okay. So what basically happens is that in this case, they're basically saying, while I'm sleeping, all I'm going to do is to make sure that maintain the basic network presence, and that any new TCP connections that I receive are honored. All other traffic I'm going to ignore. So it only provides a limited set of functionality relative to what we had requested. But kind of, so unlike Somniliqui, which basically handle everything, this one does kind of a limited functionality. this basic concept has been around for quite some time. Some of the early works were kind of this nature. So what's happening, therefore, is the following: that so through the WAN, through the subnet router, there's a box which is running a sleep proxy, and then there are a bunch of clients where kind of applications are running, and then they have this background stuff. Let's see. So that's a sleep proxying system, and then they kind of also do some data logging, and they also kind of do monitoring. So sleep notification on a client registers with the operating system, and what happens is it starts receiving information about when the client is going to sleep. At some point in time, the OS would alert the sleep notifier that it is going to sleep. The sleep notifier then informs the proxy that the machine is going to go to sleep, and it provides a list of TCP ports which the machine was listening on. So these were all applications which were listening on some TCP port. What it does is it sends this information via a broadcast so that it doesn't even need to know who is the sleep proxy. It just advertises it. There may be one or more machines which are on the network which are providing the sleep proxy service, and so no configuration is needed for that. Upon receiving this notification, the proxy adds machine M to the list of clients, and then what it does is it has to somehow begin to pretend at this machine. So remember, I talked about this ARP protocol. The problem with the ARP protocol is that, so the ARP protocol, if you recall, is about mapping IP addresses to MAC addresses. Now let's say suddenly my machine disappears from the network, it is going to sleep, and a proxy machine has to pretend on its behalf. So we need to somehow let everyone else know that the mapping from IP address to MAC address has changed. That is, this new machine is going to be acting as this guy. So what it does is it basically sends out a special ARP packet so that all future Ethernet packets are going to be redirected to M. So it basically tells the Ethernet switch that the mapping has changed. Okay, that this IP address is no more at MAC address number 1, but rather it has moved to MAC address 2. And so what happens as a consequence is any future packets arriving for M are now actually coming to S. So that is the redirection part. So S responds to all these packets as if it was M. It therefore is able to maintain M's packet presence, network presence. Sometime later, some remote client is going to send a request saying, okay, I'm SSHing into this machine or contacting the web server there. And what it does is it basically at this stage it starts waking up. So what's happening? Yeah. So at this stage, this sleep proxy is going to start the process so that M is woken up. And so S examines the packet, finds out it's a TCP request destined to a particular port. So it examines, is this a port which M was interested in? If M was interested in it, then it wakes up M by sending a WakeOnLan packet. And then M wakes up and then takes over the connection. And then M sends out another ARP probe to redirect the future traffic back to M. So that's the set of things. And meanwhile, what the sleep proxy does is it basically just delays the handshake. So kind of the idea is that it, as the client is trying to connect to it, it kind of keeps it hanging on until meanwhile M has woken up, and then kind of transaction continues. So this is kind of the basic strategy. It obviously doesn't, like I said, doesn't handle the full stuff. My only new connections are being handled, and then the M is woken up. Any existing connection data on that, it doesn't serve them. So it basically works very well if you have kind of a server type setup and someone like that initial SSH that you are doing or a new HTTP request. But if the machine went to sleep and you had an existing connection, If you send further traffic to it, it's not going to honor that. Okay, it will keep sleeping. So it's a limited form of proxy, but that's what they created. So there are a variety of issues that come up in a solution like this. What may happen is there's a bit of a race condition type situation. I requested the machine to be shut down. The sleep proxy has to take over, but the sleep proxy may not be able to take over in a timely fashion. Okay, so so it's possible that sleep proxy has not taken over in time, and there's a flip side also. Sleep proxy, while the machine is going down, there is still going to be a time when the packets will keep coming to it. So we have to hand over or do this transfer of responsibility in a very clean fashion. So that's one issue. The other issue is how does, when M has woken up, how does S know that M has woken up? Again, WakeOnLan does not provide support for it. So again, they kind of resort to some additional techniques to make that happen. So there's a lot of messiness which comes because the protocols were never designed for this kind of a redirection to happen. So this sort of takes care of that. Yeah, what are the other issues? Yeah, the other issues which come up in terms of the ARP handovers. I'm going to skip these details, but the main point is that there are a lot of tiny little details that they had to kind of deal with to make this thing work. Additionally, what they did was they provided a web service. So kind of the idea is that, so this was done at Microsoft Research. The idea is there's a website, you could go to there, authenticate yourself, and then essentially cause your machine to be woken up as a last resort. So you can type your name on this machine. Essentially at that stage, the sleep proxy transfers the state back to your machine. So this is kind of there. Everything else fails. This is kind of the last resort. So this is how their system is kind of organized. So you can wake the machine up through this application interface, but otherwise, if things go well, you SSH into your machine. That SSH request causes the proxy to transfer the state back to your sleeping machine, and things kind of take over from there. Or so you can run various kind of servers and all. What you cannot do is that if you had let's say, an SSH session already running, the machine go to sleep, you hit a key, a new character goes out, that's not going to wake up the machine. It's only a new request which wakes up the machine. So using this system which they deployed, they found, they did a study and they found what are the kind of things which cause problems. Okay, so what are the things that cause wastage of energy? So one of the things that they classify as something called crying baby syndrome. And kind of the idea is that sleeping machines are often woken up by remote clients, which unnecessarily. Okay, so that's one issue. Another one is there are often applications that introduce that prevent a machine from going to sleep. So this is what they call as applications that induce insomnia. And they had some pretty interesting examples of this. So like for example, there are applications like virus scanners and all that they kind of prevent stuff. They also had an example of, I think it was Adobe Flash or Adobe Reader or something like that, which for some reason would open up connection to speaker or the microphone or something. I think it was a speaker, so it was not sending anything out. I think Adobe Flash, it would open a connection to the speaker. It won't send anything out, but it would prevent kind of the PC from going to sleep. So they identified these kind of like cases where an otherwise idle machine was not going to sleep. They deployed it on a pretty large scale at their lab and kind of steady thing. Main thing was in an operation over a year, they saved around 10 megawatt hour. 10 megawatt hour is 10,000 kilowatt hour multiplied by around 15 cents a kilowatt hour. So you can compute how much they saved. Not a whole lot. This kind of deployed it in the sort of lab setting. So some other findings that they had: most machines sleep most of the time. 20% of the machines slept very poorly in their setting. The crying baby syndrome, a small subset of remote machines caused a lot of wake-up requests. What do you think it might be? what machines tend to wake up machines most often? Think again, enterprise, what might be happening there? Yeah, maintenance type machines, right? I mean, they are going to be the one. So, so some machines, so these are mostly servers which were automated testing and probing and all that were happening. At UCLA, it also happens. There are campus network operation centers periodically scans all the machines. Okay, so just for looking for open ports and stuff like that. Who causes insomnia? So many of them are IT applications, but some of them are caused by program bugs and legacy drivers, which would cause essentially prevent the machine from going to sleep. Okay. So another issue which comes up is there are a lot of applications nowadays which are what are called as persistent cloud applications. So things like Dropbox, and they are designed to overcome the NAT/firewall issue. So what I mean by that is the following. So let me ask you the following question, okay? So we all work behind firewalls, but remote servers are still able to connect to us, right? Let's take Skype or let's take Dropbox. When on one machine I upload a file to Dropbox, that percolates down to all my machines, even those which are behind firewalls. But since I'm behind a firewall, then obviously there is no public IP address. So how do these applications work? How is a cloud server able to reach a machine which is behind a firewall, behind a NAT?
You both have to contact the external.
They both. So it's an outgoing connection. The problem with this outgoing connection, therefore, is that I cannot go to sleep. Right? The machine is going to wake up, kind of sync back in. So unfortunately, what happens in this particular case is that when we have these kind of applications, and there are many of them now, which basically have an outgoing connection, then it kind of so these are outgoing connection for the purpose of checking whether there is an incoming connection, and that basically again causes problem with this whole proxy idea. Okay, because we ourselves are waking up to check whether there is something coming to us. So in this particular case, again, kind of we need some sort of more sophisticated proxies to be able to handle this stuff. So the experience from kind of their deployment was the following: that simple reaction policy, as in kind of just keep track of what ports were open and listen on them. Insomnia, that is applications that prevent sleeping is kind of a problem. They found users rarely access their desktop remotely. So this is something which sort of often you hear, why don't you put your PC to sleep? I will work from home and access my computer. Okay, but at least in their setting, apparently that wasn't much of an issue. IT management related traffic was a big culprit. And kind of their take on that was that perhaps these need to be scheduled more intelligently so that maximize the sleep time. They also talked about that perhaps sort of redesigning some of these applications and all could kind of also, and they also found that even with this solution, where now they have a sleep proxy per subnet as opposed to sleep proxy per host, even then they found that a lot of complaints from their information from the IT department, because this additional burden of maintaining a sleep proxy for it to be reliable and all that was perceived as too much work. So I guess one message out of this thing is that any solution like this also needs to take into account kind of the management complexity, which sort of kicks in as a result. And even though this was a big step forward, a thought experiment which the very same group at Microsoft had proposed was the following: what if instead of doing all of the sleep proxy and these kind of work, we had the following solution? We offered every user that you put your machine to sleep, whatever savings you will have, you will get a share of that savings. Okay, So essentially monetary motivation. If I were to tell all the students in my lab, this is the baseline, you reduce it by X percentage, that's whatever the saving is from that, you are going to get a third of that. And kind of the notion was that many people will therefore be more diligent about putting things to sleep. So that's kind of and that's the flip take on that, which is perhaps instead of complicating the IT tasks, perhaps motivating the users better might be part of the solution also. Okay, so I'm going to stop at this stage. There are a few more slides remaining on this theme, which I'll pick up next time. But main things to cover again, kind of recap, sleep proxy notion, which is kind of the current way of doing things. I'm not very familiar with what happens on the Windows side, but like on the Apple side, it's a very seamless ecosystem right now, if as long as you're using everything Apple. Okay, so your laptops go to sleep, they have network presence. I suspect something similar does happen on the Windows side now, which is things go to sleep, network presence is there, you're still able to reach stuff, services get advertised, and everyone is kind of happy until things don't work. Linux, unfortunately, is a little bit of an outlier on this one. I think to this date, things don't work very seamlessly because they're dealing with a lot of very different technologies out there. Proxy at this stage, so you could have proxy on the computer, and that's combined with proxy on the switch or the router. That's sort of the Apple solution, and sounds like also the solution on the Windows side. You could have the Microsoft type a sleep proxy server, which is kind of a dedicated machine where things are being stored. One approach you'll see next time around is VMs have a big role also in this thing. So you can imagine solutions being created where virtual machines are the proxy. They are kind of representing you. So we'll pick this thing up on